Hello and welcome to EESC 315. This is lecture 2. Today we'll be talking about how an EIA report is put together. So we'll talk about the generic type of EIA table of contents. We'll talk about the different types of technical disciplines. We'll talk about it from the sense of something you might see in a textbook, but then we'll also get into the site C EIS, which is our case study, and we'll go through that table of contents and the organization of that document. We'll talk about this both from the perspective of how you would write an EIA if you're going to, and how you would read one if you're going to review it and try and find the information you need. So that brings us to the topic of different technical disciplines or components and the linkages among them. Okay, so let's get into it. So what's included in an EIA? How are they organized? How are they written? These are the things we're going to talk about. Our assignments in this course will loosely follow an EIA structure. So in other words, we're not going to write an EIA, but we're going to analyze one, and we're going to follow that same structure that we would see in the generic EIA to look at the site C EIS in particular, and to ask ourselves, did they follow what we consider to be the best practices? Did they miss anything? Did they do anything really well? When reviewing an EIA, remember, you don't have to just be critical. You can also look at the parts that they did really well and the things where they communicated well and helped the reader understand. Before I get into this lecture, I just want to mention that there are a couple of other lectures that you might want to view. These are sort of optional. These are from another course. These are from EESC 418. So if you've taken this course already, don't bother. But if you haven't, I think these two lectures would be quite useful to you as you write this report throughout the term. So you don't need to go find these. They're linked from Canvas. So these are a couple of lectures that I did last semester, and I think they would be fairly helpful. So if you need any help writing a report, if you're not 100% sure how to avoid plagiarism, when you need to reference things, you should go take a look at those. So with any links that I put throughout this presentation and other presentations, you don't have to write them down. I'll also link to it on Canvas if it's something important. Okay? So let's talk about the EIA technical components, also known as disciplines. Those two terms are used fairly interchangeably in the EIA world. So environmental effects will include a lot of different scientific disciplines. When we talk about assessing environmental effects, we're talking about land, water, air, health, and lots of subdisciplines within those topics. And so I'm going to go through 3 different ways of organizing that information. So I'll go through the technical discipline organization, in other words, the land, air, water, health type of breakdown that I just talked about. And I'll go through a typical report organization, and then I'll also go through the Site C report. It'll be really important for you to be able to navigate that report as we go through the semester. And then finally, I'll go through effects linkages. And I'll just note that for effects linkages, I'm going to replay the video that I recorded, the audio that I recorded in the lecture from last year. And the reason is I'll be doing this throughout the semester at times where I've got a fairly good audio and slide deck from last year. I did record them throughout the term even before COVID came along, and I just think that when I'm standing in front of a classroom, the lecture becomes a little bit more natural, so hopefully the audio will be a little bit more natural sounding for you when I replay last year's talks. So I'll only do that where the information really hasn't changed or I don't need to update it. In a lot of places, like the first half of this slide deck, I've reorganized things just having looked back at trying to improve the course from last year. So in some cases I'll be recording this year, and in some cases I'll be recording from last year. Okay, so hopefully that works and it's not too different for your ears, but let's see how it goes. So within any discipline or any component, so for example, within the water components, you'll find a component called water quality, and that's really looking at the chemical and biological makeup of the water. Similarly, within the air quality, you'll have an air quality section that looks at the chemical makeup of the air. And within each of these specific technical disciplines, there will be usually an appendix report to an EIA, a technical appendix. And within each of those, you'll find the types of information that you see on the slide here. So this is just a generic outline for an environmental impact assessment technical discipline. In other words, the environmental impact assessment itself will be contained in another volume in another report, which will link to these technical appendices for supporting information. So this term, we're going to mainly focus on the technical appendices. We're going to specialize on one specific discipline per group, as I mentioned in the introductory lecture. And so within an EIA or an EIS, you'll find a report that has this type of outline. So we start with an introduction. So this is just a broad overview of what we hope to achieve with this assessment. So some background on our study area, maybe on the issues that need to be assessed, on the type of development that we're assessing. And keep in mind that there will be a detailed project description elsewhere in an EIA. So we don't need to get into the full description of the project, really just the parts of that project that have a potential to affect the type of environment we're looking at. So again, if we use a water quality example, we don't need to go through an entire EIA project description, just that part of the project that can have an effect on water quality. So now we're taking the information from a project description or from some other volume, and we're making it specific to our assessment. So the objectives, what is it that we hope to figure out by the time this report is done? And then the scope, what are the bounds within which we're working? What are we looking at? What are we not looking at? Then we'll get into the methods and approach, and this is where we get into a detailed description of how we're going to do the assessment. At this point, we're not going to be presenting any findings. It's really just the how. So scoping, key issues and linkages. What are the key issues that we're looking at? How are we going to look at them? Our study area will generally have some well-defined spatial boundary. So usually if it's a water component, it can be a watershed. If it's an air component, it can be everywhere that the air plume or air dust or any sort of air effects can travel to. If it's wildlife, it might be the range of a certain species. It's really what is that spatial extent that makes sense for our assessment. It is good if those are well aligned. In other words, if a hydrology component has a different spatial extent than a water quality component, it can be sometimes difficult because if the water is flowing and we're changing the flow of water from one project downstream to a community or to some receptor, logically, if we're changing the flow, we're probably going to be changing the chemistry as well. And I should note that with all of the topics I'm talking about today, we will be going through these in detail. I'm just giving an overview of how it's all organized and how it all fits together before we get into the details. So pretty much everything I'm talking about on this slide will have either a lecture or part of a lecture dedicated to it later on in the semester. So time frames and snapshots. We need to look at different time frames for a project. Usually that's pre-development. What does the environment look like before any sort of development occurs? And this might mean looking into the past, or it might mean looking at the present before a project is built. We need to look at the construction phase. Almost every project that would have an environmental impact assessment will have some sort of a construction phase. And then we look at operational or lifetime snapshots. And depending on the type of project, we might look to closure. So for example, a mine, a mill, a pulp mill, any sort of a large factory, something like that should have a closure phase identified with a closure plan and a way to restore the land back as close as possible to natural. And we would look at all of those time frames either individually or as a long sequence, but we need to lay out in this section of our report how we're going to look at those time frames. Next is indicators and thresholds. So for everything that we assess, there must be some way of measuring it, of quantifying it, so that we can make a comparison from before and after. So this usually comes with something that we can measure and apply some units to, and hopefully we have some sort of a threshold. So that can be something like a water quality guideline, an air quality guideline, an effects threshold for some biological species, generally something that has a number attached to it that can say, yes, this is fine, or no, this is not fine, we need to mitigate it. And next, we'll lay out a basic approach for how we're going to do the effects analysis. In other words, how are we going to use these indicators and thresholds to do our effects assessment and come up with some sort of significance rating. Next, we'll talk about a baseline study. And in a lot of environmental impact assessments, the baseline is in a completely separate report. but it does make sense if the report is not too long to include the baseline and the effects assessment in the same report, because really what we're doing in a baseline is we're going out and measuring the natural environment in its present state so that we can later compare an affected environment to that baseline environment. In other words, how do things change? Do they get worse? If so, how much worse and for how long? But in order to do that, we need a really good characterization of the present day. And the baseline, when I say present day, doesn't just mean today. It generally means over a number of seasons, over a number of climatic conditions. How does the natural environment behave and what are its characteristics in this present time frame? So that will entail usually some field methods for just about every type of environmental study. It may also include laboratory methods too, with soils, water quality, air quality. Typically samples will be collected and sent to a laboratory, and we need to describe how those are measured. And then some sort of a data analysis. A lot of different types of effects assessment will include statistics or modeling or some other numerical method that will help us make sense of very large data sets and try and distill it down into some meaningful information. Next is the actual effects assessment. So now we've described how it's going to be done. Now we lay out what we find. So this is basically our results or discussion section. And within that section, we might lay out 3 different development scenarios. So the base case is what is on the ground today, and it's a little bit different from the baseline. The baseline is really just measuring the natural environment. The base case might include some other projects. It might include an existing project that is going to be expanded upon as part of this impact assessment, but really it includes any project which is approved and is almost certain to be built, so that we can then do our next assessment case, which is the application case, where we add the effects of the future project onto what is either existing today or is likely to be existing by the time our project comes along. And finally, we'll do a cumulative case, also known as a plan development case. This is where we take any future forecasted project that might come along and add up all of the effects from existing plus the project we're applying for, plus any other project that anybody else might apply for. In other words, it's a cumulative effects case. Next, we'll talk about any sort of mitigation. So if we've done an effects assessment, often we'll find some adverse impacts, and as a practitioner, we'll go back to the proponent, or if we're working as the proponent, we will want to apply some sort of mitigation to make the effects smaller or make the effects go away. So for example, if there's a discharge to the environment, either an air discharge or a water discharge, and that discharge will cause some sort of an adverse effect, we might go back and install a water treatment plant or an air scrubber or some other type of mitigation to prevent these emissions from affecting the environment. And so there's lots of different types of mitigation that can be applied, and this is really a big part of an environmental impact assessment, is figuring out what is the right mitigation to stop or minimize the effects on the environment. After mitigation is applied, we'll look at what are the residual effects. In other words, what are the effects on the environment that either can't be mitigated or can't be mitigated economically, or for some other reason we still have effects left over at the end of this project. Based on that, we'll need to apply some level of significance. And keep in mind that the point of an EIA is to identify any significant adverse impacts. Significance is a really important word here. We'll talk a lot more about that later in the semester. Another big term or another big concept is uncertainty. With any sort of future prediction, which is basically what all EIAs do, there's going to be some uncertainty associated with those predictions. And regulators and stakeholders really need to know what level of uncertainty we have when we do these predictions. So as a practitioner, you might do an EIA and you have a pretty good idea that you've made some predictions, but those are maybe plus or minus 50%. Or they might be really uncertain. They might be plus or minus an order of magnitude. Well, you need to communicate that really clearly to other people who will read your work so that they can understand and make an informed decision based on your work. Finally, we'll recommend some follow-up monitoring or adaptive management. Again, because we have this uncertainty, it doesn't mean the project can't be approved. What it typically means is that there needs to be follow-up monitoring and the project can be adaptively managed so that that uncertainty is reduced over time. Again, we'll have a whole lecture on adaptive management in February. So looking at some of the technical components, these are sort of the generic breakdown. In other words, this is what you might see in a textbook or just sort of a general EIA that doesn't have a lot of really unique effects. This is definitely not the case with Site C, but it's a good place for us to start. So I've broken it down into air, land, water, and health, and this is often how an EIA is broken down. So within air, we have air quality, which is essentially chemical concentrations in the air, chemical concentrations of particulate matter that can settle out of the air, that can be ingested into lungs, etc. So we call those ambient concentrations, and this relates back to any emissions, emissions controls. This is usually calculated by modeling. Then we have noise and acoustics. And with most projects, we'll have a fairly noisy construction phase while we have heavy equipment working. If it's a mine or some other large industrial project, we might have ongoing noise throughout the life of the project. We'll also have greenhouse gases, particularly if it's an oil and gas project. But even something like Site C has greenhouse gases. For example, any project that uses a lot of concrete will generate a lot of greenhouse gases in the process. And so even though a project might not be oil and gas, it might have a heavy fleet of heavy equipment that are processing the land. It might generate a lot of concrete. It might have a lot of shipping up. For example, if the project is up in Northwest Territories or far from civilization, all of these things generate greenhouse gases. And even though the project might be mitigating it down to zero, it might be a net zero project, we still need to go through a large assessment to understand exactly what are the greenhouse gas emissions and what potential effects could that have on climate change. Moving into land, we start with terrain and soils. Really, of course, that is the land itself. How will this project change the terrain? Will it be a large earth-moving project? What will it do to soil quality? Will they stockpile the soil and save it and reclaim the land when they're finished? Or will the soil be damaged? Often if soil is damaged, it's pretty much damaged forever because soil regeneration is such a slow process. It's really impractical to regrow soil. So, even though you could on an infinite time scale, within the time frames that we care about for an environmental impact assessment, you can either stockpile that soil and reclaim it, or it's going to be an adverse impact. It could also be an adverse impact, but stockpiling it is certainly a way to mitigate that. Next is vegetation and wildlife. These are very broad categories, with typically, depending on where the project is going to be located, there will be multiple unique species that are assessed within those categories, and those unique species might become valued ecosystem components, which get their own assessment, and we'll see that is the case with Site C. We then have archaeology and paleontology. So this is looking at any sort of remnants from past societies, from past animals, anything that can tell us about the past. And of course, if these are damaged or destroyed, there's no restoring these either. So typically there will be large archaeological surveys done on any sort of large development. We then have resource and traditional land use. This typically relates to indigenous communities. And so this can both relate to field studies and speaking with communities and trying to understand what were the resources of this land in the past. Another one is visual aesthetics. This is typically done for a very large project where the impact is large enough that you're actually changing the aesthetics of the landscape. And so if you think about forestry, any sort of mining, any very large earth-moving projects, visual aesthetics become very important. Next is the water components. So we have groundwater, also known as hydrogeology. So that's any groundwater that can be affected by the project, and that really falls into two categories. One is groundwater that is withdrawn, and the water can be withdrawn for use, or it can be withdrawn to make an area geotechnically stable, for example. But either way, that what that means is that you're depleting the groundwater as a resource. And the other side of the groundwater, or hydrogeology, is any contaminants that can get into the groundwater and pollute the groundwater. So there's typically two types of assessment done for groundwater. Next is water resources, and again, this has two sides to it. Part of it is most projects will use some water, or a lot of projects will use some water, and that can mean diverting a stream into a reservoir. It can mean pulling water out of the water cycle in some other way, for example, groundwater or capturing rainwater or any other sort of water use. But the other side of that is the effects on the downstream environment from any water diversions that, for example, maybe a river is diverted so that a project can be built in that area. Next is geochemistry. And of course, the big effect that geochemists often look for is acid mine drainage or any sort of other acid generating process. So if geological materials are disturbed, they might have high sulfides, and when those sulfides are brought up to the surface, they can become oxidized, generating sulfuric acid and leaching metals. Next is water quality. Water quality looks at the chemical composition of any water that's affected by the project, and that can be things like nutrients, metals, ions, bacteria, and other things that would make our water less useful. The next two are sometimes classified with water and sometimes put in with health, but these are benthic organisms and fish habitat. So typically we have two sides to these organisms. One is we look at any direct effects to them, which can mean physical disturbance to their habitat or any sort of process that will physically disturb them. On the chemical side, that's often covered under health. So if there are some chemical constituents that can affect the health of fish, that's usually covered in the category below. So the final category is health, and the health component looks at all of the results from the previous other disciplines. So in other words, any air and water discharges will have some effect on human health, ecological health, wildlife, and aquatic. And so the health components typically are known as a human health or ecological risk assessment, and these components will look at any changes from the previous components. And we'll talk a little bit more about that when we talk about linkages. Okay, and I just also want to note that there are lots of other topics that are associated with an environmental impact assessment. So looking at social impacts, economic impacts, engineering aspects of the project. So for example, in the project description, there will be a lot of engineering information that describes how the project is going to be built. There's a regulatory side to it, consultation. There will be large consultation reports included with an EIA, and indigenous interests. Now, I think a lot of that is covered in EESC 314, so I'm not going to get into that material. I'm really going to focus on the technical aspects throughout this course. But keep in mind, if you haven't taken EESC 314, that there's a whole other side to environmental impact assessment, which is all of the stuff that surrounds these technical disciplines that we're going to be focusing on in this course. So when it comes to Site C, I showed this table in Lecture 1, but I'll just quickly go over it again. So the technical studies are shown below, and you can see they're fairly similar to the technical disciplines that I mentioned in the previous slides, but these are now just getting a little bit more specific to what you would worry about in a dam construction project. So geology, terrain, and soil. Surface water regime. Surface water regime is just another word for water resources or hydrology. It's really how does the river water levels change, how do the volumes change with time. Water quality is as I described. Groundwater regime in this case is how does the changing water level in a river, because it's being turned into a reservoir, how does that change the surrounding groundwater? Thermal and ice regime. This is unique to Site C. There are not many EIAs that have a thermal and ice regime assessment, and we'll talk more about that later in the semester, but the big reason for that is because as a dam, it changes the thermal regime of a river, it changes how the temperature changes with time, and it can change how the ice behaves. And that has a big implication for the Wood Buffalo National Park and the Peace Athabasca Delta, which is very far downstream, yet still affected by upstream dams. So again, I'm going to leave that because it's a huge topic, but we will come back to thermal and ice regime later. And then fluvial, geomorphology, and sediment transport. Of course, if you build a dam on a river, you're going to alter how the sediments are transported, which has implications both for sediment buildup in the reservoir itself, but also for the constant evolution of the river all the way downstream to its mouth. You're going to change how those sediments are transported, which has implications for how nutrients are transported, for how the channel is formed and how it changes over time. Next is methyl mercury. In most EIAs, this would be covered under water quality, but because it's a hydroelectric reservoir, there are some specific issues around Methylmercury generation. So in a reservoir, as sediment settles out and becomes bed sediment, we can get organic carbon, and that can be degraded, turned into methane, where it combines with any present mercury, forming methyl mercury, which can then bioaccumulate up the food chain, and we have a methyl mercury issue caused by that reservoir. So this is a fairly common process that we see with hydroelectric reservoirs, and so in this case it gets its own part of the assessment. Microclimate is also a very interesting topic. Building a reservoir, in other words building a lake where there was previously a river, will change the climate in the surrounding environment. Similarly, air quality, it's a major construction project with lots of concrete, heavy equipment, so there are air emissions, and similarly we have noise and vibration from that same equipment. All of that needs to be assessed. And then another unique discipline for the Site C EIS is electric and magnetic fields, of course, because we have generators and transmission lines. So this is something that also is a fairly unique assessment for this energy project. So at this point now I'm going to flip over to the Site C EIS on the government website, which is also linked from Canvas. This is linked under resources, not within this lecture in terms of Canvas organization, but you will see a link there. And I'm going to go through the actual Site C EIS fairly quickly. Okay, so here's the Site C EIS. If you follow the link from Canvas, you'll come right to this page. This is the old CEA website, Canadian Environmental Impact Assessment. So this is the previous agency before the Impact Agency came along. But this is still the website where the Site C EIS is held because the EIS was done about 10 years ago. Okay, so we start with the overall organization. So this is fairly typical of an EIA or an EIS. We'll have a cover letter that introduces the document to the government, an executive summary, which, as I mentioned in Lecture 1, I hope you've had a chance to read. It'll really help you with the rest of this project. An important thing that not a lot of EIAs have, but is good to have, is this table of contents and authorship. So for each of the volumes, there's an individual table of contents, and I'll come back to the table of contents shortly, but something that's fairly important is the authorship, because some EIAs really don't list all of the individual authors, so there's really not a professional person accountable for each part of it. However, this is, I wouldn't say it's unique to BC, but it's certainly more prevalent in BC than other places where I've worked. And so with each section we have a contributor and credential, and so I know a lot of you are going to be looking for PGO designation or RP Bio, and in some EIAs it's an absolute requirement that somebody who's got a P something or other is listed. So a P Eng, a PGO, RP Bio, P Ag, all of these credentials really state who is responsible and what is their professional accreditation of the authors for each section. So that's kind of an important thing. Coming back to the overall table of contents, so volume 1, and I should mention that most EIAs have several volumes. A volume is typically presented in hard copy as 1 or 2 3 to 5 inch binders, so big documents. Within that we have an introduction to the overall project. So at this point we're not looking at any individual technical component, we're really just looking at what is the Site C dam, what does it entail. And there will be some appendices for this volume, but we're not getting into the assessment appendices yet. It's really just all about the project description. What is happening with this project? How is it planned? How will it be mitigated? And then volume 2 in this case, it can vary, but typically volume 1 is project description, and then volume 2 can either be a baseline assessment or impact assessment. But now we're getting into the technical work. And so we'll have again a table of contents and authorship. And so in volume 2 we have again methodology, which I previously called methods and approach. And then we have cumulative effects assessment, environmental background, which is what they call a baseline. And so I've mentioned it before, but I'll say it again. In the world of EIA, there are a lot of different ways to say the same thing, unfortunately. There's not a lot of consistency. Surface water regime, also known as hydrology, water quality. And so now what it's doing is it's going through each of the different technical disciplines. But coming back to this master table of contents in the HTML form, what we see is that for most, if not all sections in that EIA document, we have a technical appendix. And the technical appendix will be a standalone report, typically prepared by one or more different consultants, and it will look at the technical discipline or technical component that relates back to the EIA. So we'll have an EIA document that ties it all together, that goes through the assessment, and then a technical document that really has all of the details about how that assessment was done. And so keep that in mind when you choose your technical discipline. Is really what you need to pick is one of these technical appendices. There will be some sections in the EIA body document that you'll need to be concerned with, but most of what you'll need to be concerned with is this technical appendix document. And so I'm going to open one to use as an example. I'm going to choose Appendix P, and rather than open it online because it's a large document, I'm just going to open it on my computer. And so the reason I chose this one is because this is actually the document I worked on, so I understand it pretty well. And I want to show you a specific complexity of EIAs that can make it challenging to navigate the documents. So these days they're organized a lot better than they used to be, believe it or not. EIAs used to be even more disorganized, but now what we have is a volume. Within that volume will be a type of document. So volume 1 was project description, volume 2 was technical work, and then within volume 2 we have lots of different technical appendices. And so this is Appendix P, volume 2 Appendix P. But now where it gets a little bit complicated is within even a technical appendix, we have multiple parts. So Appendix P has 3 parts. This is volume 2, Appendix P, part 1. If we go to, say, page 113, now we start volume 2, Appendix P, part 2. And we can go to page 414, and this is the start of part 3. Now, unfortunately, these are typically not linked very well, and the reason for that is that the proponent or the consultant will take multiple documents and sort of mash them together into a PDF, and then there is no document that sort of hyperlinks within the PDF. So you have to sort of fumble your way through these sometimes to find out how they're organized. And to make it even more complicated, if I go to, say, 245, this is the start of the appendix for volume 2, Appendix P, part 2. So Appendix P, part 2 has its own appendix. In fact, it has 5 of them. So volume 2, Appendix P, part 2, Appendix A. So you have to really drill down into the details, and you will all do this as part of the course. You'll become intimately familiar with one of these documents. You certainly don't need to do all, but one of the documents on the EIS. So coming back to the EIS listing, have a look at these. You might want to just open the documents and have a look at them, see if something interests you, something you'd like to spend the next 3 months reading about in detail. So I'm going to move on now. So most of the remainder of this EIS will not be part of your project, but it's still good to know what is included in the document. So volume 3, now we're getting into land and resource use, economic assessments. So we're really looking at the socioeconomics in volume 3. In volume 4, we have heritage and health effects. And in volume 5, we have asserted or established Aboriginal rights. So these are quite different types of information. But keep in mind, for your project, you'll focus on the technical appendices in volume 2, and then certain parts of the volume 2 assessment. So somewhere in this volume 2 assessment methodology and environmental effects assessment will be a section that ties together the technical appendices that you care about. Okay, so the third type of organizational structure that we'll look at is a linkage analysis. And this is not exclusive, they're not mutually exclusive, so you can have the report organization that we talked about and you can have linkage analyses shown within that report. It's really just another way of showing how effects translate from one to another. And this is really showing, for example, how the water quality might affect the health of a human or some sort of other species. So in other words, now we're not looking at it from a land, air, water health breakdown. Now we're looking at it from how one thing might flow to another. And so as I mentioned earlier, I'm going to use last year's audio for this, so I will now transition to that and then come back for the end. What a linkage diagram tries to answer is there a direct or indirect link between a project activity and an environmental effect? So if you build a dam, is there going to be a direct linkage between building that dam and a VEC? Obviously there is, since it's a VEC, but it's nice to show, you know, what is that pathway and be a little more specific. So these are a bit more specific about what type of effect we're going to be considering. Second thing is there a link between one technical component and another? So for example, the air quality team will do a Kelpuff model or some other type of dispersion model, trying to understand if they're digging up dust, where's that dust going to end up? Another team of ecologists will look at if that dust lands on bearberries, is it going to be taken up? Are people going to come along and eat it? And then the human health risk assessors will assume that somebody's eating those and will do a health risk assessment incorporating the dust fall that eventually happens. And so that linkage is essentially air quality to vegetation to human health or something like that. Whatever that linkage is, it's useful to show, particularly for people who don't want to spend years trying to figure out an EIA, because they're huge documents. As if you've seen the appendix, the list of appendices for Site C, there's a bunch of different volumes. Each one has appendices. They can be really hard to navigate, especially for some poor person who just lives there and isn't a scientist and just wants to understand what the heck is going to happen here if this thing gets built. So this is just a bit of context. I'm going to show a bunch of linkage diagrams. I just wanted to show what they're sort of representing. So this is the Jackpot mine expansion. We did this EIA about 8 years ago or something like that. And just for scale, that's about 10 kilometers. So this is a big mine. It's like 20 kilometers across. This was an existing mine and they were expanding it, basically tripling its size. And so obviously a mine like that, it's going to have all sorts of adverse effects that we need to consider, not least of which is there's a river here that will no longer be a river. So they need to actually rebuild aquatic habitat elsewhere. But the way we try and simplify that is to look at a project activity, and we'll list a bunch of project activities. What is the environmental change we care about? What is our VC? And which component is going to assess it? And then there will be other linkage diagrams showing all the linkages between components. So I'll just show a few here. So hydrogeology, what does hydrogeologists care about? Basal aquifer depression, depressurization.
They essentially have to suck the groundwater out before they can mine, otherwise it's unstable. Overburden dewatering, they have to dewater the land that's going to be mined. External tailings facility area, they're going to generate tailings and put them in a tailings facility, and then ultimately backfilling and reclamation of the mine. So these are the main things that the hydrogeologists are looking for. And again, there's not really much detail at all here. Each of these is going to be covered in excruciating detail in the EIA document. But this is just a little bit of a guide to the reader that says, here's what we're assessing. These are the environmental changes that we're concerned with, and which one of these can lead to which changes. These are essentially their VCs. They don't call them VCs, but you can think of them as VCs. It's just a different jurisdiction. And then these are the linkages from hydrogeology to other components. So it's going to affect the flow of groundwater, is going to affect the flow of surface water, it's going to affect the chemistry of surface water, and it's also going to affect the terrestrial vegetation, because now you're dewatering. And of course, if you're dewatering a pit, you're not simply just dewatering the pit, it's going to have a cone of drawdown around it that can extend for quite a ways, depending on how hard you're dewatering and what are the characteristics of the aquifer. So that all needs to be well understood. In other words, if we want to dewater a pit that's 500 meters wide, are we actually going to dewater a landscape that's 5 kilometers wide and basically dry up and kill all the vegetation in that area? So first step is trying to understand if that's going to happen. If it is, the next step is then to mitigate it. In this case, the mitigation was a barrier that would essentially stop the groundwater shortly beyond the mine's boundary. And that way that cone of depression is very confined to a small area. Surface water regime, they didn't call it surface water regime, they just called it, I think, surface water quantity or hydrology. But again, same types of things: dewatering, in mine pits, diverting a river, dewatering an aquifer, withdrawing water. This is actually water use for the mine. Most developments have some sort of water use. And then an integrated closure plan. These are the changes they're looking at: changes in sediment yield, changes in flow and water level, any erosion, changes in water balance of other lakes, so that's being drawn down possibly, and then changes in open water area. Changes in open water area will change the evaporation, it'll change habitat, and of course these feed into fish and fish habitat. If you're changing the flow of water, you're also changing the fish habitat. Whether or not you're changing the fish, that will be answered in the EIA, but you're absolutely changing their habitat. It'll change the water quality, and again, terrestrial vegetation, and we need to know how it's going to affect all these other components. Water quality, so this was my section of the report. What are the big issues? So these are the same. Essentially, we're just looking at the hydrologic and hydrology models, but now we're also concerned about the seepage quality. We're concerned about the creation of pit lakes, and then another big one is acidifying emissions. So any type of development that has combustion, whether that's a mine fleet or any other sort of vehicle fleet, even I'm pretty sure on Site C, if you look at their acidifying emissions, they would have had to account for all the buses carrying workers, they would have had to account for all the scrapers and heavy equipment in the area. But what happens is with any sort of combustion, you will also combust some nitrogen and sulfur. Sulfur comes from the diesel, so you want to do low sulfur diesel. But when you combust either nitrogen or sulfur, what will happen is in the atmosphere it will turn into nitric acid and sulfuric acid and come down as acid rain. So that's a huge potential issue that you need to deal with. And again, as it shows in this linkage diagram, pretty much all of these can apply to pretty much any one of these environmental changes. And again, what do we really care about? It's going to go to human health, wildlife health, aquatic health, fish and fish habitat. In the end, I hate to say it, but nobody cares that much about water quality unless it affects something living. So that's really where we want to go with these, is if you're concerned about this effect here, acidifying emissions, you're going to need to figure out which of these components you really care the most about if you're going to go looking for effects. So aquatic health. Aquatic health is usually based primarily on the water quality assessment, but also changes in air quality, which then affect aerial emissions. And now we're not just talking about aerial emissions of nitrogen and sulfur. There's also emissions of PAHs, metals, other compounds in the stacks or fleet emissions that will then come back down as precipitation. So that will change water quality. Going to chemical changes in concentrations in fish tissue if it's something that bioaccumulates. And then people will eat the fish, so you need to send that to human health. But aquatic health will do their own assessment and say, here's what it means to the fish, and then it will continue on to human health. And then similarly, it affects human resource use. So this is separate from human health. This is going to ask, have we impacted people's ability to hunt, fish, trap, and use the resources, regardless of whether or not those resources themselves are damaged. A good example of that is methylmercury. For the folks doing methylmercury, when a dam is built, you're almost certain to get some methylmercury generated, depending on, the biggest factor is how much of that land has organic carbon in it. It's actually not really related to the mercury content. It's very slightly related to that, but the big factor is how much labile organic carbon is in the sediment. And so the dams that were flooded prior to about 1990 probably, this was not understood at all. And so all they did is set a dam in a river valley, flood the valley, and now we've just flooded a huge store of peat, muskeg, vegetation, trees, everything. And in fact, Williston Reservoir, I'll digress here a little bit because it's kind of related to our project. Williston Reservoir is upstream of Site C. Williston Reservoir was flooded in 1967. They didn't chop down a single tree, as far as I know. I don't know how many they did, if any, but they left a lot. That I can tell. I went fishing there when I was about 18, and they have these what are called deadheads, which are trees sticking out of the water, and worse yet, they have trees that are like a foot below the water. So you'll be driving along in your boat, and it'll just go whack. Your motor will hit one of these trees, and you didn't see it. But that was just standard practice back then. Build a dam, flood it. Now all of the trees for sure will be removed, as much vegetation as they can, and you can see this in their assessment. I don't remember how much of it they said they would strip, but generally any really labile or reactive store of carbon, you want to get rid of that. Otherwise you're going to have anoxia, you're going to have methyl mercury production, and a whole bunch of other issues. So back to why I'm talking about this. Methyl mercury at the concentrations we care about is extremely toxic to humans, but it's actually not toxic to the fish. So you can have a fish that has methyl mercury concentrations in its tissues, in its fats, that human would be severely harmed if they ate, but the fish actually has no effect. The effects on fish have to be, I think it's like several orders of magnitude higher before there's any actual effect to that fish. And the reason for that is because methyl mercury affects neurochemistry. Fish don't have a whole lot of neurochemistry going on. Okay, this I think is the last one. It's a fish and fish habitat. Kind of the same story. It's going to look at all of the different effects. Pit development, closure activities, stream diversions, construction, clearing, muskeg dewatering. All of these things have some potential impact on fish. These are all the different environmental changes that can go on to actually affect the fish themselves. So this is the DCs for fish. And now, if you affect the fish, you affect the resource use. People will no longer trust the fish, even if you haven't actually damaged them. You can have a big effect on resource use just by simply being in the vicinity and doing some development. Traditional land use, people don't want to go out on the land if you've disturbed it too much, and to biodiversity. So all of these kind of flow from the fish assessment. And human health, this was interesting. It looks like they either missed it or omitted it. At some point I'm going to ask the person who did it why it's not in there, but they didn't have one in the EIA. So that's actually kind of common. You'll go to some section and you're looking for something, it should be there, it's not, there's no reason. Unfortunately, that just happens. They're massive documents. I have no idea why they missed that. It was really unusual, but I thought it was kind of interesting. It's just not there. Questions so far? Yeah.
Does that make a difference in the Google EIA if there's a section like that missed? Would they kind of refute it and send it back?
So what's interesting is, I'll refer to this specifically to the Alberta process. In the Alberta process, the Alberta government has to do what's called deem it complete. So once an EIA is deemed complete, you're kind of done. But there's several rounds of questions back and forth to get to that point, and they go over everything with a fine-tooth comb. And looks like they never cared or never noticed. But the answer is almost always, if you're missing something, they'll just send you back a supplemental information request, and they'll say, we couldn't find the linkage diagram for human health, either provide one or provide justification why it's not necessary. And it's kind of standard. Provide us what we want or tell us using science-based evidence that we don't need it and here's why. And those questions can be, I mean, like thousands of questions on an EIA because they're huge, right? They're looked at by 20 different experts. Each one has 50 to 100 questions, and so that's a huge part of the process. We are going to talk about information requests and supplemental information and stuff later on. Okay, so you might have a linkage diagram to start with that has everything under the sun, and you look at it and you go, well, actually, all of these processes are hypothetically possible, but in this case, it's actually not really an issue. And so that's called breaking a linkage or deeming a linkage invalid. And I'll just let you read that. This kind of describes what sort of process will end up with an invalid linkage. So either it just doesn't apply because of site-specific circumstances, or because the proponent knows that this is going to be an issue and they've already just said, we're going to mitigate this. So a good example is tailings dams. Most mines have a tailings dam. Everybody knows tailings dams are awful. So before they even think about doing an EIA, the engineers will plan, we're going to do water capture, we're going to put in interception wells, we're going to do an in situ barrier 10 meters deep around it, and put in all of these mitigations so that when it comes to the assessment, you look at it and you go, well, there's not even a linkage there because they've got everything under the sun actually applied as mitigation. And so those are engineering controls. That's kind of the most common type of mitigation is an engineering control. Water treatment plant is the same. If you can treat the water down to water quality that is acceptable, that is sort of similar to background water, completely within guidelines, totally healthy water, you really don't have a linkage anymore. I should mention one other thing. Another approach that proponents will do is to just start off and say, do a kind of a rapid assessment, do kind of a scoping level assessment, tell us what the linkage is going to look like so that we can decide what are the big things we need to mitigate. And that can kind of help them because they do have finite resources. And so if you can list 10 things and 4 of them they can mitigate for the same price as mitigating one big thing over there, they'll probably try and mitigate 4 of them for that same price. It really depends, but it's just a different approach to do this. Okay, and I'll just show a few examples. So this one, the linkage is broken by inserting mitigation. And this is kind of just some general text, so I'll leave it. You can read it later if you want. And then another interesting condition is a linkage that is valid for part of your system but invalid for others. And this relates back to your scoping. You want to scope what's relevant, what's necessary. Preferably, you don't just say, you know, we're building a sewage treatment plant here and it's in the vicinity of 30 rivers, so let's assess all 30 rivers. You want to say, you know, it's discharging at this location, it'll have a near field effect and a far field effect, and so our study area is, you know, our linkage is valid for this part of the river. And it's not about getting out of things, it's really just about focusing your time and energy and resources on what really matters. Okay, and the last thing I wanted to talk about today was conceptual models. If you're already familiar with conceptual models, you probably don't need me to show you a bunch of diagrams to explain what they are. If you're not that familiar with it, check out the video I have from my other course, which is linked here, but also linked from Canvas. So it's only 6 minutes long. It just kind of goes through some examples of what conceptual models look like. But I wanted to talk about some EIA specific information about these models just to end this lecture. So conceptual models will be in the lab assignment, of course. So you're free to use any type you want as long as it communicates what you're trying to get across to, in this case me, but pretend it's the stakeholders or whoever it is you're trying to communicate to. So I've put a few pointers on here. I'm sure there's more. Interestingly, I looked in several EIA textbooks. I could not find conceptual models in the index. If they're in there, they're listed in some term I've never heard of. So I couldn't find any reference material on this. I was very surprised. So again, show what's relevant and nothing more. And that's just like the tips for scoping. This is really just an extension of scoping. What are the issues? How can we describe them? How can we illustrate them? So all details of the conceptual model should be addressed in the assessment. In other words, don't put something on your conceptual model if you're not going to assess it. If you're putting stuff on your conceptual model and you're not assessing it, you're confusing people and you're giving them false impressions about what they're going to see. So it's just really good practice to not have anything on there. If it's important enough to be on your conceptual model, it should somehow relate to your assessment. Now I say at the bottom, the converse is ideal but not necessary, meaning that not everything in your assessment has to be on your conceptual model. You can assess 50 different things, maybe 40 of them are very straightforward. You don't need to explain to every stakeholder what the other 40 are, but there's 10 that you really are, either they're really important, they're really complicated, they're really sort of novel, you need a tool to explain them. That's what you want to put on your conceptual model. Oh yeah, and I put here, so reading an EIA often is like searching for a needle in a haystack. And if you're putting stuff on there that's not necessary, you're essentially tossing more hay on that haystack. So try and avoid that. And then another point is conceptual models don't need to be pretty at all. They need to be accurate. But at least for the ones you're putting in your assignment, I don't really care if they're, you know, done by a nice GIS tool or anything like that, as long as it's straightforward and it shows what's necessary. So I should go back and mention here, of all of these, basically you can probably pick the ones that I did myself versus the ones that I had help with. So this, obviously, this was done by a GIS person. This was done by a landscape architect, believe it or not. This was done by a drafting team. This was done by a modeler, not me, but basically this is actually done in Excel. This was done in PowerPoint by a modeler. This was actually generated by the model itself. It actually outputs that figure. Who did this one? GIS analyst, GIS analyst, GIS, GIS, drafting, me, textbook editor. So you can see that depending on who does it, you'll get a very different level of quality. And if you're using these for public consultation, it is important to actually put that extra bit of quality into it. So, for example, I would probably not go to a public consultation meeting and show this figure. I would have somebody turn it into something a little nicer like that. So that's really the only time it's important. The government actually doesn't really care, so if you're thinking of them as your stakeholder, I wouldn't go to a whole bunch of extra effort to do something really beautiful. Okay, so that's it. That was quite a lot, but keep in mind that almost everything we talked about today, we are going to talk about in more detail as the semester progresses. So I look forward to getting into the details with you over the next 12 weeks or so, and hopefully this sort of sets the stage for how an EIA comes together, how the writing is done, how the organization is done, and how all the different technical components relate to each other. Okay, see you next week.